Hello everyone, today is December 8, 2025, and today we're going to look at this LeetCode question number 156, binary tree upside down. It is called upside down, but basically it's more like a rotated clockwise to the right by probably 90-degree-ish there. So you'll see if you rotate this thing to the right, you got the Y up there, and then this is reconnected to Z for the left side, and this is to the right. So everything rotated to right by 90 degrees. So here they are like the rules here. So basically the left one will become the new rule, and the right original rule becomes the right, and this becomes the left there. So that's exactly what's happening. Basically, from the rule connected to the right to the left, and then do the rotation. So this is a one level example. It looks trivial. In a two layer example, the question gave, it sort of looks like this there. So basically, it's still like if you rotate 4 would be the new rule, and you rotate it 90 degrees, and this part, the 2 will become like the new right rule, and this part will become the left rule there. So that's pretty much what it does there. But what happened to the right node there? So do we also need to do rotation? So here's the rule that the question gives us. I mean, this example is, I don't know if intentionally vague there. If there's not a single node in this case, there's a little structure. According to the rule, this structure will just keep the same as is there. So the original left becomes the new rule. The original right is an original rule becomes its right, and the original right becomes its left. So that's the rule, pretty simple. And then it doesn't talk about like on the right internal structure, does it rotate or not. So basically, I would say just don't overthink too much. The right would just keep as is there. So we would just reconnect this two, put this one, and then rotate. I mean, rotate itself is also a concept to human. It doesn't really matter to a computer as long as you recognize this as a rule node, and there's a left pointer and a right pointer, and the right pointer, whatever on the right side, just stay the same as it is there. So that's what it's doing. So from this example, we can see this on the left side is definitely like a recursion. So if we do the reconnecting here, like a 4 points to 2 and to 5, as it's right, as a new right and new left there, and then now goes to 2 as the subtree there, and then it points to 1 and points to 3. So that's the reconnect is happening. Whatever on the right stays the same, but we do a recursion on the left node there. So basically, this suggests this would be like a recursive function call to itself somehow. So let's try to implement it. So basically, like for any kind of recursion, if anything like is in the end state, then we need to, it's usually the first step. The pattern is like you return something, that's the base case. And then you work on the more general case that reduce the problem into a smaller problem. So basically, if a rule itself is none, that means like there's nothing, it should be none there. So the new rule will also be none. There's nothing else to do. And if the rule is left is none, that means when would the rule left be none there? So you have to be the leftmost rule node to be like to be none, right? So that means like basically this would become the new rule. So we return rule itself there. So this number 4 will be the leftmost rule, but we can also say any leaf node its left right is its left node is like it's not there. So however, as we go, we see the recursive function will never goes to the right side because they're all on the right. Only the left node would have a chance to get to here, being called by the recursive function. So yeah, if it's lucky enough to get into line number 13, that means we are general row. We're not like a empty row, and we're not like a leftmost leaf row there. So our current rule would have like its own left and its own right, and its left is guaranteed to be not null, because if it is, then you will not pass the if statement here. So then what we can do is to recursively call this function. So because this is a class method, so it should be a self dot this upside down binary tree function, and then the rule call on its left. Is that the only parameter that's taking? I think so. Yep, that's the only parameter that is taking, is returning like a new node. The new node will be the new rule of the left tree there. So it will go all the way recursively, all the way to the leftmost node and return this node. So this left node is returned it, and then, but just let's think about like using one as the example. So this is working on the left tree. There, it's gonna return this whole thing, which is already reconnected according to these three rules there. And it's gonna return 4 as the new rule. But like 1 is still pointing to 2 here. It does the reconnection, but it's still pointing to the 2. So basically this part, this whole part become the new rule there. Then what we need to do is like the current rule would become the right, would become the right child there. So left, the current rule, it's left. This is the only way that we can point it to this node here, because the one that returned, which is what we call left here, is pointing to 4. Now we're working on this node here. So this node's left child, so the new rule will become the right child of this subtree there. So basically, we're looking at rule number 2, and its right child will be equal to the current rule, right? So basically, it's drawing a pointer from 2 to 1 here. And then we work on the left child. So this is still like a rule dot left, which is the node number 2. Its left child should point it to the right side of the original rule. So its left child will point it to the current rule's right side there. So and the right side will just leave it unchanged there. So this points to here, this points to here. So this is what you mean. It's a little bit confusing, I know, but probably gonna stare at the picture several times before it can make sense. So let me talk about this again. So roots, this is the rule. Its left is node number 2, and node number 2's right, it will be the original root, and node number 2's left would be the original root's right. So will be node number 3 here. And now, so we already connect like 2 to 1 and 2 to 3. Then we need to put this original link from the current rule, because it's not supposed to like have a reverse pointer pointing up to the string there, putting up to the tree. So the next step we just like break this. So set root dot left equal to null, and also set root.right equal to none there. And now we can return like left being like root number 4 as the new root. So that's pretty much it. Like this is basically like a rewriting these 3 nodes there. So the original left child become the new original left become the new root, the original root become the right child, and original right child become the left child. So this is like exactly what we're doing here. So let's try to run the test. Run a small test. Yeah, it passed. And run a big test. Yeah, it also passed. So we're beating like 100% of the solutions, meaning it's the fastest. So this is supposed to be really good. And what about the time and space complexity? So you see, we're doing the recursion there, and pretty much this is just a DFS. We're going through like each left side of the node once, but in a stack. So basically, the time complexity should be O(n), and being the number of nodes, we basically just go to the left part of the nodes. And the space complexity, so maybe like yeah, it's hard to estimate, but the size should be like O(n). Even we are going to like a half of the size is a constant multiplied by n, so that's always O(n). And the space complexity, because it's DFS, so the worst case is like you put everything onto the stack there. So then the space complexity is also O(n). If you found this video helpful, please smash the like button. It really helps support the channel. And don't forget to subscribe for more content like this. Subscribing also helps the algorithm recommend similar videos to you. Thanks for watching, and I'll see you in the next one.